Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this lecture on Advanced Transition Metal Organometallic Chemistry. In our last class, we had a detailed discussion on an important class of organometallic compounds. These are sandwich complexes, and what we saw that these sandwich complexes, though has its origin on ferrocene, but gradually it has emerged as a new group or new class of its own, with various kinds of variations observed for the sandwich complexes. Apart from sandwich complexes which contain two cyclopentadienyl or other cyclic ligands sandwiching or encapsulating the metal on both of its sides, there are also half sandwich complexes in which there is one cyclic ligand bound to metal and the vacant site, other vacant site is occupied by other organometallic ligands. So apart from this, we had also seen that in sandwich complexes it can be homoleptic, or that is the same type of ligands binding to the metal, or it can also be heteroleptic, where two or three different kinds of ring bound to the is found bound to the transition metal. These apart, we had also seen that the same ligand can bind in different fashion in sandwich complexes. For example, we had looked into examples where the cyclopentadienyl ligand was bound to the metal complex in eta 5 as well as in eta 1 or eta 3 fashions, which suggest that these ligands are very versatile and also can bind to the same transition metal in the within the same molecule in the same complex in two or more different ways. Now, having seen these sandwich complexes, we have also looked into various preparative methods available for preparing these sandwich complexes in the last lecture. Today, we are going to talk about another important class of compound. These are called transition metal cyclobutadiene complexes. Now, these is not a very simple system to look at. The name starts from cyclobutadiene and the raging controversy regarding the structure of cyclobutadiene. The question is, what is the structure, or what can be the structure of cyclobutadiene? Now, from a very simple perspective, one can write down the structure of cyclobutadiene having a cyclic four-membered ring having two double bonds. Then the question is, what is the structure of the cyclobutadiene? Is it rectangular, or is it square? A rectangular structure would mean something of this kind, and a square structure would mean something of this kind. So these has different implication. Now, if one looks at it, one can say that why would a cyclobutadiene being rectangular, because in that case there will be two long bonds and two short bonds. And that one can possibly speculate because of the presence of double bond and single bond. Whereas if this is something similar to that of benzene, where it can have a structure where all the carbon-carbon bonds are equal, then that would give a square structure with something similar to that we had observed in benzene. Now, the interesting debate sort of starts with theoretical calculations as well as spectroscopic identification of cyclobutadiene molecule, and that indeed showed that cyclobutadiene molecule by itself should have a rectangular structure. Synthetically, when one made cyclobutadiene complex of transition metals, for example, cyclobutadiene moiety bound to transition metal and isolated with some other ligand, then one found that this has a square structure. So, this debate gives rise to a very interesting chemistry with regard to today's topic, and the topic we come today is transition metal complexes of cyclobutadiene ligand. So, in order to understand what is the true nature of cyclobutadiene ligand, one has to look at its structure and bonding, particularly look at how the molecular orbitals interact or evolve by mutual interaction within the ligand, and then without beyond the ligand when it does interacts with transition metals. So, before we proceed to speak about the different chemistries of cyclobutadiene complexes of transition metal, let us sort of look at the structure and bonding of cyclobutadiene ligand and compare that with similar that of butadiene ligand, which is non-cyclic butadiene ligand, as well as to the allyl ligand which we have learned of earlier, and then see how the molecular orbitals differ so as to address this issue of square structure or its rectangular structure. Now, if one were to draw the atomic orbitals involved in cyclobutadiene, then one would see there are 4 p-type orbitals which will give rise to 4 sets of fragment molecular FMOs, fragment molecular involved orbital, p-type orbitals that would arise from the combination of various p orbitals of cyclobutadiene. So there will be, since there are 4 p orbitals, so there will be 4 FMOs. They would be psi 1, psi 2, psi 3 and psi 4. Now, so psi 1 would be all bonding in nature, hence now psi 2 and psi 3 would be 2 degenerate orbitals, and there molecular orbitals would be something like that, and the third one or the fourth one would be psi 4, which will be all the way antibonding in nature. So, butadiene would thus have 4 electrons, and the psi 1 will be fully occupied, whereas psi 2 and psi 3 would be singly occupied, each with 1 unpaired electron each. Now, this scenario makes cyclobutadiene in its square structure. This configuration is relevant when the structure is square structure, that psi 2 and psi 3 become degenerate, and thus in its square structure, what does it happen? The square structure is stabilized by binding to transition metal, as we had seen earlier, giving rise to complexes of the type this cyclobutadiene transition metal Ln, and when it interacts with transition metal, the metal puts 2 more electrons in its psi 2 and psi 3 orbitals, thus pairing them up, as a result making it a dianionic 6 electron system, resulting in the aromaticity, and as it becomes aromatic, then all the 4 bond becomes of same size, and it thus becomes a square. So, this molecular orbital diagram sort of explains how cyclobutadiene become square structure upon binding to transition metal, and it does so by accepting electron from the transition metal to become aromatic 6 pi system, resulting in equal carbon-carbon bond length. Now, this diagram is sort of starkly different from butadiene. Now, in butadiene, again there will be 4 p orbitals. However, the energy is of these orbitals would not be same as it is with regard to cyclobutadiene. So, difference between butadiene and cyclobutadiene is that there will be 4 combinations of orbitals, but this degeneracy between C2 and C3 would be lifted. So, I will illustrate this. So, again there will be in butadiene there would be 4 p orbitals, and they would again interact to give 4 MOs of psi 1, psi 2, psi 3, psi 4. So, let us take a look at psi 1. Now, psi 1 being bonding, the orientation would be something like this. Then comes psi 2, this is psi 2. After psi 2 comes psi 3. And last comes the most energetic psi 4. So, one thing to note over here is the number of nodes. So, this has 0 nodes. So, and hence this is the most stable molecular orbital, fragment molecular orbital. Psi 2 is slightly higher, it has 1 node here. Now, Psi 3 is even higher in energy than Psi 2. So, it has 2 nodes, one over here, one over here, and then lastly it is Psi 4 which has 3 nodes over here, here, here. And this is the energy order, and again the butadiene would have 4 electrons. So, that would mean that Psi 1 and Psi 2 will be fully occupied and they are diamagnetic. So, now I would ask you to see the difference between the molecular orbitals of butadiene and cyclobutadiene in its square form. So, what emerges out that in cyclobutadiene in its square form, this Psi 2 and Psi 3 becomes degenerate and they are singly occupied each with 1 unpaired electron, which allow them to accept electron from the metal center and achieving its aromatic configuration in a 2 electron dianionic form. This is an interesting observation which differentiates cyclobutadiene from butadiene, and not only in their structure but also in their reactivity pattern. Now, for a better appreciation of this molecular orbital, I would go further, and I am going to draw the structure of the allele moiety, and that would also give you a feel for how the molecular orbitals overall make a difference in terms of the binding and reactivity and as well as bonding of these ligands. Similarly, allele has a 3 p orbitals, and that would give rise to 3 FMOs. The first one obviously would thus be Psi 1, which would be something like this. It will have 3 lobes. The second one likewise would be Psi 2, which will have 1 node and higher in energy than Psi 1. And lastly, we have Psi 3, which will have three nodes. So, this has 0 nodes, this has 1 node, this has 2 nodes. Now, pi allele ligand in its neutral form would have 3 electrons, and the configuration of that would thus be. So, allele in its neutral form is a radical, and hence it is highly reactive, and when it interacts with transition metal, similar to what it becomes monoanionic by accepting a electron from the metal in its Psi 2 or homo-orbitals. This phenomenon is exactly similar to that of butadiene as it interacts with the metal. There are 2 singly paired orbitals which individually takes 1 electron each. So, one can see a similarity of the neutral allele ligand with that of the neutral butadiene ligand in its square geometry, the similarity is that neutral allele ligand is a radical or a monoradical, and a square geometry cyclobutadiene ligand in its neutral form would thus be a diradical, as is shown over here. On the other hand, butadiene which does not have this degeneracy is fully diamagnetic. Psi 2 is lower in energy, much lower in energy than psi 3, and as a result both psi 1 and psi 2 are fully occupied with paired electron. Psi 3 is sort of unoccupied and represents the LUMO of this ligand. So, in this discussion I have brought out the difference in the structure and the reactivity that has its genesis on the atomic orbitals of the cyclobutadiene, and I have also made a thorough comparison of the way these atomic orbitals interact with each other to form the molecular orbitals with respect to their acyclic just butadiene counterpart, and then went on further and made a comparison of this acyclic butadiene and square cyclobutadiene MOs with that of the allele MOs that we had earlier discussed. So, now we are going to look into these transition metal cyclopentadienyl complexes in much more detail, particularly from their synthesis standpoint as well as from their reactivity standpoint. Preparations of or isolation of cyclobutadiene, direct reactions of cyclobutadiene in with metal precursor came out later, but even before that, a method available for preparing these cyclobutadiene transition metal complexes whereby dehalogenation of dihalo cyclobutadiene ligand. So, let me illustrate that. The first available method way back in 1959 was obtained through preparation of dehalogenation of dihalocyclobutene. The reaction of dihalocyclobutene, where there is only one single bond and two chlorine atoms, with nickel tetracarbonyl, results in elimination of nickel Cl2 . Okay. So, distance of these are 140 to 145 picometer, which is these carbon-carbon bond lengths, and nickel carbon bond lengths are about 199 to 205 picometers. This compound is kind of really stable, air stable. and occurs at red violet crystals. This is an important synthesis reported by Craigie in 1959. Now, the stability of this complex can be ascertained from the electron count, and that shows that it itself is a fully 18 electron valence electron compound, and one can do the counting by simple neutral covalent method, which will give 4 electrons for this, and then 1 for the chlorine, 5, nickel is 10, so 15, and then another covalent 16, and this is a dative bond which will be 2 electrons. So, overall this is a 18 valence electron compound, and this being 18 valence electron compound, no wonder this compound is air stable and can be crystallized under ambient conditions. What we see, the power of stabilization of a ligand by complexation through transition metal is very much evident in this synthesis. Cyclobutadiene in its square form is diradical in nature. So, that means it should be extremely reactive. However, when they complex with transition metal, it acquires 2 further electron and becomes aromatic, and then it is so stable that it can be stabilized by coordination to transition metal. The compound which is shown over here, that thus would be an example of half sandwich complex in the nomenclature that we have discussed earlier. And with this, I would like to bring on the curtain on today's lecture. To summarize, we have looked into various important class of organometallic ligand, which is cyclobutadiene, and we started off by looking at this ligand right from the point of understanding its structure. According to simple spectroscopic evidence, or according to simple organic chemistry knowledge, cyclobutadiene would have 2 double bonds, and as a result one would expect a rectangular structure with 2 long bonds and 2 short CC bonds. But when these compounds of cyclobutadiene are stabilized and with transition metal, one sees a fully aromatic square structure where all the CC bonds were equivalent, and that gives us to understanding how the atomic orbitals interact to form such a structure. And so, we have in the beginning of the class, we have looked at the origin for the structural variation that addresses this controversy or solves the issue of rectangular versus square structure of cyclobutadiene. Not only we have looked at that, we have looked at the cyclobutadiene MOs with respect of simple butadiene MOs as well as with respect of allele MOs, and then made a comparison in terms of their reactivity that may arise from there. In addition to that, we have also looked at the preparative methods available for preparing such beautiful class of cyclobutadiene transition metal complexes. So, we are going to discuss more of these preparative methods that are available for preparing this fantastic class of cyclobutadiene ligand in the next lecture. I again thank you for your patient hearing, and we will look forward to have some more intimate discussion on these cyclobutadienyl transition metal complexes in the next lecture. Thank you.